Morning Science Peeps, this is Mr. F for Birdman Science Lessons, and this is the second installment in the four-part series on the scientific method. In part one, we covered the scientific method, its parts, use, and how it's of value to us in the scientific community, and how that compares to other subjects and the way we get information in those. This second part is going to deal with experimental design, as well as identifying variables, and how variables will come into play to help you better design experiments that will really answer adequately the questions you have laid out before you. Okay, and not just that, but come up with sound science and sound methodology to get to your end result or conclusions. Okay, all right, so let's begin. What do we need to know to design an experiment correctly? Okay, a lot of people think that it's very difficult. It's something that takes a lot of work. You know, there is a framework that exists that if you follow it correctly, the pieces that you put into it will fall in so neatly that by the end of it, you're going to have a well-crafted experiment, and you're going to have data that's sound and data that really speaks to your hypothesis and why you're doing it, the experiment in the first place. Okay, so first thing we need to know is what's a variable, and what are the different types of variables that we are going to need to know in this endeavor. All right. So a variable, first of all, is something that changes in an experiment. All right. If you look at the word root is vary. Well, to vary means to change or to alter over the course of something's existence. So a variable is something that's going to change in our experiment. All right. Let's look at the three types of variables that we're going to see in science to get a little more comfortable with how we would then use them to set up our experiments. Okay. So the first type is going to be an independent, or also known as a manipulated variable. All right. These are also going to be referred to as the IV or the MV. Okay, so that's just the shorthand version, but they stand for independent or IV or manipulated MV. Okay, so what these variables are, and these are very important variables in a scientific experiment. So, but these are variables that you're going to change. And by you are the scientist. You are the one conducting the experiment. And the reason why you're going to manipulate or change these variables is because you want to see a response. You want to see what happens as a response to these changes. Okay? So this is one of our types of variables. All right? So let's look at the next type. The dependent or the responding variable, designated DV or RV. Okay? Generally we use IV and DV together as a pair, and we use MV and RV as a pair. They really mean the same thing. You just have to know your audience, and some might not be familiar with one or the other, so you just have to make sure they understand before you start using these designations in the long term. Okay? So what is the responding or the dependent variable? These are the variables that are measured. Okay? And what do I mean by measured? So these are the ones that we observe. Okay. What do I mean by that? Well, this could be something that you literally measure with a scale. You measure with, let's say, a ruler. You use certain sensors or apparatuses to get numbers, numerical constants for something that you're observing in your outcomes in whatever you're doing. Okay, so this is something that is a product of your changes. So what happens in this is you change something in your study, and what that does is it affects something else. And that is dependent upon the change you make. And that's where the namesake comes from, the dependent or the responding variable. It responds to the change or is dependent upon the change that you make. In the same way, that independent variable is independent of anything. Okay? That really is what you change. So that is not dependent on anything. All right. So the independent variable is going to be what you change. It then affects something that you then measure, and that measured quantity or that measured element is going to be the dependent or responding variable. Okay, so those are two of the three variables that we're going to see in a scientific experiment in our design. So what's the third one? Now, the third one is a control variable. Now, a lot of times students mix this up with what's called a controlled experiment, and I'm going to talk about that in a little bit. But what a control variable is is basically, this is a variable that has the absence of a treatment. Now, what do I mean by this word here? What do I mean by a treatment? So imagine a scenario where you are growing plants with 3 levels of fertilizer, okay? Let's say you have 10 grams of fertilizer in plant 1, 10 grams in plant 2, or 20 grams in plant 2, and 30 grams in plant 3. Well, how do we know how effective those fertilizer amounts are? Well, we have those treatments, which are the levels of fertilizer. We have to compare them to no treatment to see how much they affect the plant growth. And that's when we use our control variables. Our control variable is our trials or our experimental groups that do not have the treatment given to them. So in this case, instead of the fertilizer and water being added to the plants, you would just add water with no fertilizer, or in this case, with no treatment. Okay, that's your control variable. If you don't have a control, how do you have information to compare your measured values to? Okay, so you could have some great results, but what's the stock situation? What is the normal environmental condition of this plant with just garden variety water? Okay, so that's something that is a vital part to add to your experiment. So with these 3, the independent or manipulated variable, the depending or the responding variable, and the control variable, you have the pieces of information now set to start looking at what it is to design an experiment. So let's go forward. Okay, so let's do this example together. All right. So here we have a study, and somebody tabulated data, moisture compared to the distance from the water. Okay, so in this particular scenario, we are going to have a scientist that had basically a pond here. Okay, so this is our pond. And what they did was they measured outwards from the center a certain distance. And then what they had was at 10 feet, 20 feet, 30 feet, and 40 feet. And they might have done this in different radii from the pond. Okay, maybe those are our 3 trials. Maybe that's trial 1, trial 2, and maybe that's trial 3. And what they did was they sunk a probe in to a certain depth, the same depth every time. And by doing that, they were able to measure the moisture levels in the soil. Okay, so we're not going to talk about hypotheses or purposes or anything here. I just want to use this data to help you understand the design of an experiment. Okay, so let's say each one of these different radii outward from the pond, and this is going to be your 10, your 20, your 30, and this is your 40. This is your 40 feet from the pond. All right. So you see the data on the scale there, or on the table there. But there's one line. There's one line which is up here, which you guys see here. It's the water. Okay. So the water is basically going to be, let's say in here, it's the soil moisture in the water, where it's not actually a field, it's water. Okay, so if we look at these, let's take a look at what we have and let's identify what our variables are here. Okay, so remember, our independent variable is what is changed. What does the scientist in this case, what does she change? Okay, so if you look at the distance from the pond, okay, you're going to see 10, 20, 30, 40 feet. So in this case, our independent variable is going to be the distance from the pond. Okay, so that's what the scientist has chosen to change. And if you look, this is going to be, if you look right here, these are going to be our IVs, and then all these here are DVs. These are all dependent variables, and this is going to be basically the amount of H2O, or in essence moisture or water vapor in the soil that's measured by a certain sensor or a device that they probe into the ground a specific distance. Okay, so now we know what's changed, which is the distance from the pond, and then we have the amount of moisture that's measured at each one of those points along the way, and we are getting a data set from this. Okay, and so then the last thing is, what is the control? Which one has no treatment? Which one has no distance from the pond? Well, if we look at it, it's our first line here. It's the water. Okay, so our control variable are the measurements basically taken in the pond. okay, in the pond soil. And there is soil beneath the pond, obviously, so it's going to be taken there, okay, or not in the field, okay. That's going to be where that control variable. So that data will be compared to the data that you see in the 10, 20, 30, and 40 foot from the field distances, okay. All right, so let's take a little bit more. Now, we have an experiment running here. We do not want to see variables. We do not want to see variables other than what we want to change. We only want to change the distance. We don't want to add anything to this experiment that will further create variations, okay? So what a controlled experiment, and that's the key word here. You're going to see this a lot. This is going to be a key term, controlled experiment. Okay, there's a control variable, which is what we compare our dependent variables measurements to. But the controls, what we call controls, are going to be what we keep constant throughout every trial at every point that we do in this experiment. So let me give you an example of what's controlled in this experiment. We are going to use the same pond. Okay, I'm not going to go to another pond and do the same thing unless that's what I want to set out to do for my study. For this particular study, we're using the same pond and we're doing multiple trials. Okay, all right, so in this case, the same pond. We also want to take measurements at the same depth. Okay, so in the same depth, sorry about that, at the same depth will give us very consistent readings. Okay, because if we changed our depths here, what that would end up doing is giving us different numbers. That our 10-foot measurement will have a different reading at trial 1 than trial 3. If, let's say, we went down 1 foot for trial 1 and we went down 2 feet for trial 3, that wouldn't make sense. And then those pieces of information would not be able to be averaged. Okay, so that would cause greater variation and thus, worse or less reliable results. Okay, so the same depths of measurement is what we would end up using. Okay, we'd use the same probe. Okay, you would try to use the same probe to measure the moisture or the water in the soil. Don't use different ones. Perhaps they weren't calibrated exactly the same. They might not read exactly the same. There might be slight differences. So you want to try to maintain everything as consistent as possible. Okay, all right, another thing, you might want to have the same researcher, the same person doing all of these trials. Okay, so then if there is an error, it's a consistent error that then you can account for at the end of your study. Whereas if you have 2 or 3 different people doing these, you might have 2 or 3 different approaches, which might add error in different areas, and those areas might give you vastly different data. Okay, so same researcher. Okay, and then the other thing that you want to make sure that you're going to be doing all this information on and all this gathering is, you want to do it on either the same day or same time of year. So if you do it at the same time of year, even a couple years in difference, you know that by this time of year it's going to have a certain amount of moisture in the soil, and you can compare how it differs year to year, okay? And on the same day, because up to that point the pond as a whole, or the area as a whole, has gotten the same amount of moisture, so you're not going to have introduced variables in your experiment. And by introducing those different variables, like if you do it on, let's say, if you do it on different days, or you use different researchers, or let's say you use probes from different companies, or you use different depths, what we end up doing is we introduce what's called an experimental bias. And what you end up doing with that is the results get skewed in a certain direction. Okay, so, or they get skewed in a direction that isn't really a direction. It's all over the place. If you use different days, maybe one day after a week of sun, and let's say your next day is after, let's say, 6 inches of rain just fell, that creates a bias. Okay, so what you want to do is you want to keep as much controlled and consistent as possible. Okay, all right, so that's what we're looking at here. And then as you see, this experimenter is going to be able to take the averages, and why this person did 3 trials is a very important thing to do. So this is something that we call, it's repetition. Okay, why do we repeat trials? When we repeat trials, what we do is we get more true values. Okay, so by getting true values, what I mean by that is when you average out these numbers, you take the weaker, maybe with numbers with slight error in them, and you average them out with the true numbers. So what you end up getting is a truer, more realistic value. And in the end, what this comes down to is accuracy. The more trials that you do, the more accuracy you will then get. Okay, and that's what we strive for, is having the least amount of error, the most accurate numbers, so then when we draw our conclusions, you have the greatest amount of reliability. And in the end of it, that's what we want to see. We want to see studies that are reliable. Okay, so reliable studies are going to have multiple trials. Even in this case, what this experimenter might have wanted to do is maybe take, if you see all these lines I'm drawing on the pond down here, done even more trials, so possibly done 7, 8, 9, or 10 trials in every single direction, because maybe there is a hill on this side here, maybe over here it's flat and it runs off. So either way, you're going to want to have as many trials as possible, because then that means your average here is going to be very realistic. It's going to have all your errors and your true numbers in the same average, so you'll be more accurate. And in essence, when you speak about the data, you can speak about it with more reliability. Okay? All right, so let's move on. All right, so let's do a couple examples here. And let's have you do the analysis and writing these down. And then what I would say is read it, go over it, write down the independent, the dependent, and the control variables. Pause it in the meantime, and then when you're done, unpause it and come back, and we'll review it together. Okay? So go ahead and then hit play again and come back, and I will work through this with you. Okay. Different rose bushes are grown in a greenhouse for 2 months. The number of flowers on each bush is counted at the end of the experiment. Okay? So what's the independent variable? What is changed here? What is the scientist choosing to change? Different rose bushes are grown in a greenhouse for 2 months. The number of flowers on each bush is counted at the end of the experiment. Okay, so what's changed? Well, if you guys had said to this, maybe the type or the species of rosebush, okay, the type of rosebush, that is going to be what's changed. Which ones are we looking at here? Okay, they could be ones that are known to have high flowers. There could be ones that are known to exist in different climates. In any event, they're different rose bushes. So what's measured? What's our dependent variable? What is it that is depending on what we change? All right. Well, in this case, we're looking at the number of flowers. Okay, because that depends on the type of rose bush, right? We could have a rose bush that weakly grows flowers, that does not grow too many. It just, maybe it lives in an environment where it's energy poor or nutrient poor, so it can't produce the type of flowers that it needs. Okay, so what's the control variable here? What is the control which is without any treatment? Okay, well, the number of flowers on each bush is counted at the end of the experiment. So different rose bushes. Well, in this case, it's very difficult. We really wouldn't have a control here, right? Because it's without the treatment. So we're only studying rose bushes here. So at which case, you pretty much, if there was a specific rose bush that you were comparing all of these to, okay, then you would have a control variable. So in this case, which rose are you comparing? Okay? Comparing to. Okay, so if that's the case and you have a particular rose bush, maybe a rose bush that grows in your area that does well, and you want to see if any of these other ones grow better and make more roses, more flowers, then you would potentially have that particular rose from your region. Okay, so that's going to be this one here. All right, let's look at the next. All right, read through this, work through your independent, dependent, and control variable, hit the pause button, and then come back when you're done and we'll review it together. Okay, guys, welcome back. You water 3 sunflower plants with salt water. Each plant receives a different concentration of salt solutions. A 4th plant receives pure water. After a 2-week period, the height is measured. Okay, so you water 3 sunflower plants. Okay, so those 3 sunflower plants, the same species, okay, that's a constant, all right. You water it with salt water, okay, that's another constant. Each plant receives a different concentration of this salt water, and a fourth plant receives pure water. So which ones have you changed? Okay, so in this case, it's the different salt water concentrations. I'll just put concs there for concentrations. Okay, so each plant receives a different concentration of salt water. Okay, so that's your independent variable. That's what the scientist has changed. Then the fourth plant receives pure water. So in this case, your control variable is going to be the plant that received only H2O with no salt. Okay, so the dependent variable here, okay, what was measured in the end? After a 2-week period, the height is measured, okay? The height of the plants, okay? So in this case, we would generally measure it in meters if it is going to be taller than average, let's say more than 5 or 6 feet tall, we're going to probably measure it in meters. You can also measure it in centimeters if it's, basically 3 feet or less. So you want to make sure you use the proper units on those. Okay, so those are your independent, dependent, and control variable examples. Well, let's keep going. Let's do some more practice, because if you understand it in these simple scenarios, you'll be able to apply these even in bigger and broader scenarios. Okay, let's keep going. Okay, read over this pea plant example and hit pause, and then come back when you're done and we will review. Okay, welcome back, guys. Pea plant clones are giving different amounts of water for a 3-week period. Pea plant receives 400 milliliters a day. The second pea plant receives 200 milliliters a day. The third pea plant receives 100 milliliters a day, and the fourth does not receive any extra water. The plant only receives the natural ways of receiving water, which is through normal rainstorms. The height of the pea plants are recorded daily. Okay, so the independent variable. So what's the independent variable we're looking at here? We're looking at, what we're changing is basically the amount of extra water that the plant receives, amount of H2O. Okay, all right. So the dependent variable, what are we measuring as a response to this extra water? We are measuring, like before, we're measuring height. You can also say growth, but if you do use the word growth, just take note. Leaves also grow, petioles also grow, roots also grow. So if that's the case, you might have to determine specific growth and state that if you are communicating this. So really, height is a much better use, and try not to use growth in this case, because remember, the plant grows in multiple areas, so height is what you want to look at. All right, what's your control variable here? The fourth pea plant does not receive any water, so in this case, there's no treatment or no extra water. If that plant does not receive extra water, it is basically only receiving what gets in rainstorms, and that is going to be without the treatment, because the treatment's extra additional water. Okay, very good. So let's go on. Last one. You decide to clean the bathroom. You notice that the shower is covered in a green slime. You then decide to try and get rid of this slime by adding lemonade juice. You spray half of the shower with lemonade juice and spray the other half of the shower with water. After 3 days of spraying equal amounts 3 times a day, there's no change in the appearance of the green slime on either side of the shower. Okay, so go ahead, guys, hit pause, work through this, and then hit play again and come back and we'll review. Okay, guys, welcome back. So what did you find? What was your independent variable here? What was changed? Okay, so you decide to get rid of the slime by adding lemonade juice. You spray half the shower with lemonade juice and the other half of the shower with water. So what is it? So it can be a little tricky here. So what's the independent variable? Well, the independent variable here is, in this case, whether it received lemonade or not. Okay, so the side that received lemonade was the side that received the treatment. Okay, so this was simple. There were only 2 experimental groups here, the ones that received water and the ones that received lemonade. Okay, so the lemonade was sprayed on one side. In this case, our control variable, which was without the treatment, was just the side that was sprayed with water. And what are we measuring? After 3 days of spraying equal amounts 3 times a day, there's no change, and so we are measuring the appearance of the green slime. So we are going to be looking at green slime appearance. Okay, so the green slime appearance, was it increasing, was it decreasing, was it getting clearer, was it getting more slimy? So that was what we're looking to find out in this particular example. Okay, all right, so let's take this a little deeper. All right, so as you know, the Minions are becoming world famous as we speak. So this is a little bit more of a full snapshot. Rather than just a tiny little excerpt like I did before, this is more of a full example. So we're going to work through this in the same way, except now you've got a little more data to maybe draw some conclusions on. And we'll finish up with 2 examples of this, and that'll be the end of our second installment. Okay, so Gru thinks that pop soda will increase the productivity of the Minions. He creates 3 groups of 50 Minions each and assigns each group the same task, to staple sets of papers. So his 3 experimental groups are going to be: Group 1 drinks 100 milliliters of soda pop while they work, Group 2 has 50 milliliters while they work, and Group 3 isn't given the soda pop while they work at all. Okay? So after an hour, Gru counts the number of sets of papers each group stapled, and he made the table that's below. So Group 1 produced 2,200 sets of stapled paper, Group 2, 1,703, and Group 3 produced 980. So it's nice because you have a really easy trend or pattern in your data here. So there's a great correlation to talk about. Okay, so here's what you guys are going to find out: independent, dependent, and controlled variables, and then what Gru's conclusion should be. How did the soda pop affect the number of papers each group stapled? And use the data to support your answer. So take a few moments and put the video on pause, work through these, and then hit play again, and I'll go through the answers with you guys. Okay, welcome back, guys. Hope that wasn't too bad. So let's go through the 3 variables here and what we're looking at. So what's the independent variable? What did Gru change in this scenario? Well, Gru changed basically the amount of soda each experimental group got. You had the 100 milliliters, you had the 50 milliliters, and then you had the ones that received none. Okay. So what was the dependent? What was measured? Okay. Number sets stapled. Okay, the number of sets of paper stapled. Okay, that's what was measured. What was the product of that change, or what was the response to that change? Well, what was the controlled variables? The group that received no soda. Sorry guys, no soda for you. Okay, so they received no soda. So, number 4, what should Gru's conclusion be? Well, Gru's conclusion should have been basically that the soda produced higher levels of work or higher number of paper sets stapled. Okay, that would have been the conclusion. So that there is a direct relationship between the number of stapled sets of paper and the amount of soda drank by the Minions. Okay, so those are a couple ways that you could phrase that conclusion. How did the soda pop affect the number of papers each group stapled? Well, it produced what we call a positive relationship. The more soda they drank, the more paper they stapled. Okay, so this is what we called in essence a positive correlation. As one goes up, so in this case, as the soda goes up, if you increase the soda, you will also increase papers stapled. Okay? So use the data to support your numbers. Well, you can easily say here, as you see right here, as you increase the amount of soda, so as you go from 0 to 50 milliliters to 100 milliliters, you find that you go from 980 to 1703 to 2200 packets stapled. So it goes up with every turn. Okay, so that is how the data helps support it. And it's nice because with every step you see here in the soda amount, you see a nice step in the amount here of the papers put out. Okay, all right, so that's what we're looking at with an example that takes an entire picture. Well, let's do the last one, and then we'll close this one out. Okay, so Dr. Nefario notices that his window is covered in a strange blue glitter. His friend Barney tells him that coconut juice will get rid of the blue glitter. Dr. Nefario decides to check this out by spraying half the window with coconut juice. He sprays the other half of the window with water. After 3 days of treatment, there is no change in the appearance of the blue glitter on the side of the window. So what I want you guys to do, pause this, go off and find independent, dependent, and control variables, and then I want you to decide what a possible conclusion could be based on this information. Okay, see you in a minute. Okay, welcome back, guys. So what do we find out? What's our independent variable here? So our independent variable, what was changed? Okay, so whether or not, in this case, Dr. Nefario had sprayed with the cocoa juice, whether coconut juice or not, okay? So those were our treatments, okay? Those are your two groups. So what was measured, okay? So in this case, we're looking at the appearance of the blue glitter on the window, okay? Was it getting worse? Was it staying the same? Was it getting clearer? That was what he was looking at. That was measurable. It's observable with the eyes, okay? And the control. Well, the control, the other half of the window was sprayed with water, okay? So water, which is the absence of the treatment, because remember, the treatment was the coconut juice, so the water is the control, okay? All right, so what are our possible conclusions here? It said after 3 days of treatment, there is no change in the appearance of blue glitter on either side of the window, okay? So that wasn't a conclusion. That's just an observation. That just tells you what happened after 3 days. It doesn't tell you why. It doesn't make a conclusion. So your conclusion based on this data is what? It's basically that the cocoa juice doesn't work. Doesn't clean. And that his friend Barney was kind of wrong about his assumption on the coconut juice clearing the blue glitter. So then you could go off, as we talked about yesterday in the scientific method, you can go off and run another observation, another question, and possibly study something else on this, okay? So that is our Dr. Nefario scenario here. And so if this helped, I hope this makes it a little clearer on how we look at variables and designing experiments. Our next installment is going to be proper formatting and practice with the experimental questions and hypotheses, the 3 different types of hypotheses that you will see written, and how to correctly write them, and what is a correct hypothesis. Well, I hope this was helpful, guys. Tune in next time. Take care.